I know a lot of you asked me questions on this one. This starts with probability. Now, probability, you want to make, figure out, is it asking that order matters, which is a permutation, or order does not matter, which is a combination. So that's important for you to notice first. A shipment of 150 televisions, there's your N, 150. It's okay, don't worry about it later. Okay, here's your 150. So you start off, you have a total of 150. They contain 3 defective units. So if 3 are defective, how many are not defective?
147.
Okay, these are non-defective, these are good. Now sometimes they play with the words. Determine in how many ways. Ways is different than probability. Ways is your big number. You just figure out the one part. Probability is part over whole. That's the number between 0 and 1. So I gave you the first step, figuring out how many ways, and then asking you to do the probability, part over whole. How many ways can you buy 3 of these? Do you care what order they come in, these television sets? Nope, because they all look the same. So right away we know we're doing combinations. And you want 3 of them. Can you get no defective units? How many no defectives do you have? 147. No defective means they are good. So 147, C3. You put it in your calc, 147. You go to probability, math, probability, and you come down to the NCR guide, and then you put in that, and then the 3. Just how many ways? This has got to be the big number. Okay. Now, if it was permutations, you would do your 3 lines, and you would do the first one, then 147 times 146 times 145. But order does not matter in these. Okay, how many ways? Again, can you pick 3? Any order? Out of all defectives, how many defectives do you have? 3. So, you can only do 3C3. And 3C3 is 1. There's only one way you're going to choose 3 non-defective calculators. Okay. And then the last one says, how many ways do you get at least 1 good unit? Now, at least 1 good unit says, I want a 1 good unit, 2 good units, or 3 good units. The only thing you don't want is no good units. No good units means your defects. Don't want your defects in this. So you take your total out of 150, generic, you have 150 to choose from, any 3, and you're going to subtract the one time that they're all defective. That's the only one you don't want. And then you get how many ways that will happen. The next part is just making the probability, part over whole. And actually, this piece right here is your generic. Any 3 out of 150. Any 3. And the only thing you didn't want there was the one where they all happened. But now you want any 3. This is your bottom number. So whatever the top number was, part over whole. The top number here, part over whole. The top number here, part over whole. Here's your probabilities. I wanted you to be able to remember the difference between how many ways and what is the probability. Even if I just asked you a straight out probability question, you have to figure out in how many ways first. You have to figure that part out first.
Are we going to see one first on the final?
But to be honest, I don't know how close it is to this one, but I think there's one that's kind of similar.
So no,
Yeah. I would do it I would separate it just like this. Figure out how many ways. Always figure out your bottom number is your generic. Any 3. Any 3 out of your population. Your top number is specific. 3 good ones. 3 defective ones. All but 1 defective one. But your bottom number is the generic part. any three. We okay with this? What did I call it?
Yeah, what would you call this problem? I want to look up how to do it.
It's a combinations. It's a combinations problem. This was exactly one of your homework ones too. Probably from, I want to say maybe chapter 3. Chapter 4 was the binomial one, so maybe chapter 3. And this is on the Moodle as well. I'm recording this as well, so you can always look it up. Okay? All right. Now we get into, yep, that was chapter 3. This starts chapter 4. Discrete, continuous. Discrete is the whole numbers. Continuous is everything in between. Contains decimals, fractions, and everything else. Don't worry about it. No, we're just going over your review.
Oh,
Yeah. So you want to decide if it's continuous or discrete. Discrete or your countables. 3 books on your desk. Your discrete, your continuous is how much water is in your water bottle. It could have a decimal or a fraction. So X represents the number of times Yellowstone Park's Old Faithful geyser has erupted in one day. Could it erupt a partial time? No, so then it's discrete. It's countable. X represents the amount of sugar in pounds consumed each day. Can I consume a half a pound? Then it's continuous. That's a good measure to ask yourself. Can I have a half of one? Okay, now here's your probability tables again. This brings us back to, it's like your relative frequency. The table shows the number of U.S. mainland hurricane strikes from 1900 to 2000 for various intensities, 1, 2, 3, 4, 5, according to the Saffir-Simpson hurricane scale. You know how they rate your hurricanes? And these are the number of hurricanes that occurred level 1, number of hurricanes 39 that occurred level 2, 48 for level 3, and so forth. The best way to start this table is to add up this column. How many total hurricanes am I talking about? These are my frequencies. How many total did I have altogether? So we add them up and we find out there's 165 total hurricanes that they charted in this graph. So now, to construct a probability distribution, probability is part over whole. This is just like your relative frequency. 61 over 165. And just break it down to 3 decimals. 39 over 165. And so forth. That gives you this column. This is the column that you need. The other column is optional. We really didn't use that column, but just in case you did, I'll explain that in a second. This is your probability distribution, just like your relative frequency. This has to add up to 1. If it didn't, something went wrong. Sometimes if it didn't, thing to look at is where your decimals are. Sometimes instead of writing 0.018, you might write 0.18 because you just got the numbers. Make sure they add up to 1. When you graph this, you graph the x value. This is your x-axis. This is your y-axis. It's just like your relative frequency. It's a bar graph. These are your x values. Those are your y values. Let's see if I have the graph down here. And we'll give it a title. Don't forget to give it a title. So this is my graph. An easy way to do this is like money. By nickels, by dimes, by quarters, whatever your data goes up to. If it only goes up to 40 cents, go by nickels, 5 cents. Make sure you make 0.5. 10 cents, 15, 20, 25, 30, 35, 40 cents. Make it go by money. Here's your intensities down here. These are your bars. By looking at your graph now, we can tell how much we had of each one. We had the most hurricane level 1s, which is a good thing, right? We don't want too many level 5s. We had very, very few level 5s. Those are the really bad ones. So we noticed we even had more 3s than we had 2s. This is your graphic organizer. Right? And from this, you can figure out your other things. Let me just step back a second. Now, if I ask you for your mean, your variance, your standard deviation, 2 ways to do it. When we did this, we did L1, L2. Or, if you want, L1, L2. Either way. We didn't really use this column. I'll explain it in a second. You put it in your L1.
Work either way.
Yes. Because what happens in the second one when you use this as L2, these all add up to 1. So what happens is you don't get a sample standard deviation, you don't get a sample standard deviation, you just get a population one, and that's fine. Because it can't subtract 1 from 1 and give you a sample. So you're looking for the mean, and you're looking for your population standard deviation. Now, what we did when we went through this unit was there's another way to figure out your mean, only your mean, is by taking this column, the x value, and multiplying it by this column and getting this one. If we add those all up, they came out to be your mean. However, we didn't get the standard deviation from that. So if you need the standard deviation, I wouldn't waste my time going through this column. I would just put it in my L1, my L2. But remember, when you do a 1-var stat, you have a frequency. So you have to do L1, L2. And on my calculators, it'll say your data is in L1, your x values, your frequency, L2. You have to make sure you specify L2. Otherwise, it'll just take the averages of these and give you 3 for the mean. Okay? So if you put it in there, that gives you this part of it. And then you can interpret your results. Like your mean, these are your average hurricanes. You notice that your 1s were high, your 3s were high. Which way is this graph skewed?
Right.
To the right. Follow the tail. Follow the tail. It's skewed to the right. Your higher numbers are on the left. So your mean then has to be to the left of the median. Okay, so you can just base it on that. Then I asked you to find the probability that a hurricane selected at random has an intensity of at least 4. At least 4 means 4 or greater. Come down, and now you're going to have to use your probabilities in here. Oops. At least 4, probability that it's 4 or greater. So you add the probability of 4 to the probability of 5. And I have to keep moving this, I'm sorry. I can't get this all in one. Take your 4 and your 5 and add these guys together. Okay? Add them together. Use this chart if I ask you any questions about the probability. Probability less than 2 would be just 1. There was no 0 on this, notice. Because if there's no hurricane, there's a 0 intensity, you can't have a hurricane. So this chart went from 1 to 5. This is a good one to remember. Got a lot of stuff in here. Good? Questions? No? Okay. Alright. Was this the last one in part 4? Okay. Here's another one that you probably might have trouble remembering a little bit because this was a while back. These are your binomials. Okay. These are your discrete binomials. A surgical technique is performed on 8 patients. That's your N. So there's an 80% chance of success. If there's an 80% chance of success, what is the failure? 20%. So we've got a 0.8 versus a 0.2. These have to add up to 1. So you construct a binomial distribution. Same as we did your probability distribution, we want a table of all your possible things. So out of 8 patients, you could have none that are successful. 0, 1 success, 2, 3, 4, 5, 6, 7, 8, all successful. Now, 2 ways to do this. With a combination, this is Bernoulli's combination. Start with your 8 things. We'll start with the first one, 0 at a time. Your success always comes first, then your failure. So at this point, you want 0 successes, so 8 minus 0, 8 failures. You can put that in your calculator. Second one around, you're going to do 8C1. That guy's going to change. Now you want 1 success, 8 minus 1, 7 failures. You can do that all the way down to your 8. Or, the easier way is we had a binomial probability distribution function on your calculator. And it's easy to remember. Binomial probability distribution function. Move it in there. You go second pairs, and you come down to, I don't know what letter it is. A. On the yellow guys, it's A. I don't know where it is on the 83s. And then you put in, it asks you for your N.
Just trials.
Yeah, your trials, good. Your probability of success. And then your X value. Start at 0 and then paste. After you do the first one, just do second enter and change the 0 to a 1. Second enter, 2, second enter, 3, all the way down. You don't have to redo the binomial probability. Once you paste it, it's a command. You just bring it back down and change it. I think this is far easier than doing Bernoulli's, but whichever way you remember is fine with me. We make your graph the same exact way we did your probability distribution. Okay, this is your surgeries. Let's title it. Again, these are like money. Figure this like money, your P of X, your probabilities. These are very, very, very small in the beginning because your chance of success was high. 80% is very high, it's fairly high. Would it be possible that you are that good of a surgeon and out of 8 you had no successful surgeries? No, very rare, right? So your numbers, your higher numbers are going to be towards your bottom. So in this case it's skewed left. Okay? It follows the small part of your graph. It's skewed to the left. It does affect your mean on this, but again, your mean, you could do L1, L2. Or, we have a quick way to do this. If your table is too large and you don't want to do L1, L2, we have your little formulas. Mean equals N times P. N being 8, probability of success being 0.8. And you can find your mean. Your standard deviation, N times P times Q. This table's not that bad. You could do L1, L2 if you wanted to, but you could use these as well. And then the last one, find the probability that the surgery is successful for exactly 2. Here's exactly 2. Normally we round to 3 decimal places. However, because these are so small, you have to go out to a significant digit. You can't say it's 0, because 0 means this can never happen. It's impossible. So there is a very, 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 very slim possibility of no surgeries being successful. So you have to bring it out until you hit a significant digit. I didn't have to bring out all the other ones. I just kind of carried them out since the first one was that far out. What is the probability that fewer than 2? Fewer than 2 are these 2. Add them together. Once you have your table, it makes it a little bit easier. Where you really want to use these formulas is when your end is large. Say we say we're going to do this 800 times. What would the mean be for 800? We might want to do n times p rather than do an 800 chart out there. Questions? No? Okay. What I'll do is give you this time to